This is a continuation of Chapter 8, Reactions in Aqueous Solution, and this PowerPoint is about precipitation reactions. A precipitate, which you already might be familiar with, is simply a solid that doesn't dissolve, okay, an insoluble solid. And it's relevant to this PowerPoint because there's a type of reaction called precipitation reaction in which you mix together two ionic compounds and they form at least one or more insoluble solid ionic compounds. These reactions are also called double replacement or double displacement, but to show you the basics of what happens is, again, you start with two ionic compounds and they switch partners. So I always used to tell my students, it's just easier to remember, the two outer ions end up together and the two inner ions end up together. Be careful when you're combining the inner ions, excuse me, to put the metal first. Remember, convention is in an ionic compound to always show the metal first. So another caution, the stoichiometry in this particular reaction is all 1 to 1 to 1 to 1, but clearly, obviously, it's not always going to be the case. So remember that anytime you write out an ionic compound, that you want to crisscross the charges to get the correct formula, okay? That's a real common mistake on this type of reaction. And just to kind of make sure or remind you of the states of matter, AQ means aqueous, dissolved in water. S means solid, okay, which means not dissolved in this case, all right? All right, so here's an example. You will need to get to the point where you are given reactants and you're asked to predict products and balance the reaction. So notice, all right, that the subscripts on one side, the reactant side, are completely different than the subscripts on the product side, okay? Barium has a subscript of 1 on the reactant side and a subscript of 3 on the product side. So be aware of that. And so, again, you're going to want to assign charges to the ions that are making a new compound, crisscross the charges to make sure you come up with the right product. And anytime you have a chemical reaction that seems impossible to balance, it's almost always one of your formulas is wrong, like one of your subscripts is messed up. As far as observing these reactions, this is just a really cool one. This happens to be one between, here, let me pull this down. All right, one between potassium iodide, which is a colorless solution with water, and lead nitrite, which is another colorless solution, and you mix them together. Look at this. This is your precipitate, which is abbreviated PPT, like PowerPoint. I've been doing too many PowerPoints. Anyway, so obviously, if you're going to make a precipitate, it's not always this obvious, but at a minimum, the solution will get cloudy, which indicates an insoluble solid. Just because you mix two ionic compounds together does not mean you will always get a precipitation reaction. Sometimes there is no reaction. This would be a good example of one. It turns out that if both products you make are soluble, which would be the case here, so I'm going to imagine what the products could be. And so I'm going to combine the two outer ions and get KCl. And I know they're both 1, so I'm going to combine them in a 1-to-1 ratio. And then I'm going to combine sodium and iodine. They're also plus and minus 1. Now, both of these are very soluble, okay? Which means, if you remember, ionic compounds that are soluble in aqueous solution simply float around as the individual ions. So really, all you have in this aqueous solution are these 4 ions that are just kind of floating around, waving to each other, and none of them combine and crash out as a precipitate. So there's no reaction. All right. we're going to talk about how you determine whether or not an ionic compound is soluble at the end of this PowerPoint, okay? Or in a little bit. So you remember we learned ionic, total ionic, and net ionic equations when we were talking about acids and bases. Same thing applies here. So you always want to start by writing the molecular equation. Remember, this one is molecular, which kind of gives you a summary. And then you ionize, you dissociate anything that you can, and every single reactant and product is soluble, which means they all dissociate in solution. So you've got to be really familiar with your common ion charges, your polyatomic ion formulas and charges, and don't ignore coefficient or subscripts. So this 2 goes for both sodium and chlorine, which I've accounted for here. The 2 as a subscript for the nitrate means there are 2 nitrate groups. All right, so then of course you're going to cross out the spectator ions, so everything that's crossed out is spectator. Now look what happens. Since there was no precipitate, there was no product made that is insoluble, that means there's no reaction, there's no change. So a summary of how you go about approaching these problems is, regardless of whether there's going to be a reaction, you want to predict what the possible products would be. So do your swap of ions, balance your charges by crisscrossing. Then, when you've gotten all the correct formulas, then you want to determine whether anything in there is insoluble. If everything's soluble, then you simply write no reaction. You're done. So don't leave the possible products you came up with in step 1. You just put NR, no reaction. Alrighty, so here are the solubility rules, which you have to commit to memory. And like so much of what we do, as you practice the practice worksheets, hopefully you use these polyatomics enough that it's not just rote memorization. But let me show you how to use this chart, because it can get a little tricky. Everything in the upper left are ions that tend to make the compound they're in soluble. Okay, so lithium, sodium, potassium, these are all group 1A metals. Okay, so if there's a group 1A metal, whatever it's coupled with, it's soluble, it doesn't matter. The same is true if the ammonium ion is there. All right, then some anions that are almost always soluble: nitrates, acetates, the halides. Notice that fluoride isn't, a lot of times fluoride is not soluble, and sulfates. All right, so this is probably the most important group to memorize. What are the ions that tend to make an ionic compound soluble? Ions that tend to end up in insoluble compounds: hydroxide, sulfide, carbonate, and phosphate. I always think of chalk. Chalk is calcium carbonate, and even though it's ionic, it's so insoluble in water. Now I want you to look at the right-hand side. These are exceptions, and I know this makes it more complex, but the first 2, there are no exceptions. What that means is that if you have a group 1 metal or ammonium, it is 100% of the time soluble, no matter what anion it's coupled with. Same with acetate and nitrate. The halides and sulfates are a little trickier. And for the halides, the troublemakers are silver, mercury, and lead. So if you have, let's say, silver pairing with chlorine, it is insoluble. All right? Same thing if you had, let's say, lead coordinating with iodine. Okay, again, that would be insoluble. Now, what I want you to pay attention to when looking at the exceptions for sulfate is these are the 2 that show up almost all the time: strontium and barium. they are at the bottom of group 2A. Okay, so if any question I've seen concerning that on the ACS final is either strontium sulfate or barium sulfate, and they're wanting you to remember that those are, rather than being soluble like most sulfates are, they are insoluble. Alrighty, so there's really nothing extra you need to memorize on the anions that tend to make a compound insoluble because it's redundant. Let me show you why. The exception for any of them are if they are coupled with lithium, sodium, and potassium. What are those? Or ammonium. Those are the group 1A anions, okay? So we already know they are soluble 100% of the time, so we really didn't need that exception. And these really aren't important. Yeah, those are not really important, okay? So I haven't seen either one of these much. So, and this one you already know. So there's the soluble. I strongly recommend you go ahead and print that out and have it handy, and start making note cards or something to help you remember. So here's a really easy question, but it just makes sure you know how to use the solubility chart. I probably should have said assign states of matter to each substance here. So what you would do, typically you start by looking at the anion. At least I do. You don't have to. So I would look on the solubility chart for chloride. And I'd say, okay, chlorides are usually soluble, but then I've got to double check. Is barium one of the exceptions? Is barium one of the ions that makes it insoluble? And no, it's not. So you should go back and look at it, make sure that you see that. So we're going to say that is soluble. We're going to put AQ. Now, I love it when there's a group 1 metal in the beginning because I know right away it's soluble then, regardless of what it's coupled with. All right, see, I told you you're going to see this one. Here's sulfate. They're usually soluble if you look back on the solubility chart, but barium's an exception. All right, so that is insoluble. We put S for solid. And again, here I'm happy because this potassium is a group 1 metal, and I know immediately then KCl is soluble. So now remember that if you don't have at least one precipitate on the product side, you would write no reaction. So this reaction will indeed occur because you have a precipitate. Just as we did with acid-base reactions, you are going to be asked to write total ionic and net ionic equations for precipitation reactions. And you're not really going to see acid bases. We know that strong acids and bases dissociate. So really all you're going to be paying attention to is the solubility of each ionic compound. So that's why you need to get really familiar with the solubility chart, or you're not going to have any idea what to do. All right, so here's the molecular equation. And then you would go to the solubility chart and you'd put the state of matter for everything. So we do have a precipitate. Now, remember that as far as ionic compounds go, if an ionic compound is soluble, it dissociates, right? As soon as something dissolves in water, as soon as an ionic compound dissolves in water, it dissociates. If something is insoluble, okay, which is designated with a solid symbol, right? Do not dissociate. It's not dissolved in water, so it's not going to dissociate. So you need to show it as intact in the reaction. So now look what we've done here. So we've separated the cations and anions out. Okay, notice there are 2 nitrate groups. You have got to put a charge on every single ion when you separate them out. Again, the 2 goes for sodium and iodine. Now, lead iodide is our precipitate. It's insoluble, so we keep it intact. Now, let's go ahead and cross out all of our spectator ions. So what do we have on both sides? We have nitrate and sodium. So net ionic equation, then you rewrite what has not been crossed out. And what's really cool is the vast majority of the time, the net ionic equation for a precipitation reaction shows formation of the precipitate. That's really important. Can save you a few minutes of time on a test. So most always, the net ionic equation shows formation of the precipitate. Well, I guess when I uploaded, I lost formatting. This is the common polyatomic ions that you need to memorize for the next unit test, so I didn't mean to block the question, but the question is, I'll go ahead and write it again. What is, or write out a balanced reaction, then the total ionic and the net ionic for magnesium phosphate and sodium hydroxide. Alrighty, so remember the steps of what to do, right? Combine the outer ions. So that's magnesium, and you, as always, before you write an ionic formula, make sure you assign charges and crisscross. So magnesium hydroxide is going to be one of the products, and the other product is by combining the other two ions, sodium and phosphate. I'm going to write their common charges, and I'm going to crisscross, and therefore the formula for sodium phosphate is this. So here are the products. So now I'm going to write it kind of neatly, see if I can anyway. So here are the reactants. And here are the products. Okay, so I'm going to look up solubility, and I'm going to determine if these are soluble or not. And I'm kind of hoping that you tried this on your own, but I bet you didn't. But regardless, look at the solubility chart, pause the video, back up a few slides, look at the solubility chart, and see if you can determine the solubility of each of the reactants and the products. Okay, so we can see if there's an actual reaction here. And then turn this back on. Well, okay, so I have the solubility pretty much memorized. You should after 100 years, right? So phosphates in general are not soluble. Magnesium is not an exception. It's not in group 1, so that has to stay together. And I'm going to put in S by it for solid. All right, sodium hydroxide is one of those ones I like. Sodium is a group 1 metal. Everything is automatically soluble, which means I can separate that one. And I'll put an AQ by sodium hydroxide. And now we've got the reactants. Now we've got to look at the products. Hydroxides in general are not soluble. Magnesium is not an exception. So there is our precipitate. All right, so that's our precipitate, right? One of the reactants was a solid too, which is fine. And the other product, sodium phosphate, yay. Sodium's a group 1 metal, so I know that is soluble. Be careful, the subscripts become coefficients. So now we get 3 sodium ion. I'm not being very consistent with these states of matter, am I? All right. And then 1 phosphate. Again, you got to remember the charges on these. Alrighty. Here's a summary, and this is one of those things you need to practice a lot, okay? Because you've got to have that polyatomics memorized, you have to have the solubility memorized. So, and some of them are going to be word equations. So you've got to be able to go from a name to a formula. All right, so just kind of a reminder to get to net ionics, write the molecular equation first, okay? Look up solubilities, dissociate everything that's soluble, and put an AQ by it. Anything that is insoluble, or if something is in the reaction that is a liquid, you wouldn't be expected to know. But if they showed it as a liquid, that's covalent, okay, because all ionic compounds are crystalline solids. So remember, you don't break up covalence ever. Then cross out anything that's, well, the spectator ions, okay? And then rewrite net ionic. So here is, I think I mentioned this before, but I had trouble finding it. But I spent some time, I looked. Here's a YouTube link to, it's some little saying about camels that my students have told me in the past has helped them memorize polyatomic ions. So if you want to check it out, there it is. And here's the list again of the polyatomic ions I want you to memorize. And finally, I'm going to leave this with you, and I'm not going to work that out here. I've got that, that's in Go Formative if you're in my class, but I put this here for a number of reasons. One, to make you realize, even though I already said it, that you have to be able to go from words to the formula, right? So I can kind of help you get started here. You got to do that for each of them, determine them. Then you got to predict the products. Then you have to look at the solubility chart and then write a balanced reaction, okay? And that is it for precipitation reactions.